I would like to invite Armelim Bortoleto. He has a master's degree and a PhD degree from the University of São Paulo. He also has a degree in chemistry from USP, the University of São Paulo. He is a technical consultant and he's also the accounts manager at BASF, and he has already worked at Alcoa with research in the development of biofuels, and also from the University of São Paulo. Mr. Daniel, please, the floor is yours. Good morning, ladies and gentlemen. I would like to invite my colleague Gabriela. We are going to share the floor. I'm going to talk about the NALCO water program so that we can remove fluoride in the production process to produce phosphoric acid. Okay, so I'm going to talk quickly about Ecolab. I'm going to talk about the NALCO water programs. Ecolab purchased NALCO around 2011, and so we maintain the NALCO water logo, even though it's another company. I'm going to discuss some technical concepts. I'm going to talk about NALCO POSITEK for the removal of phosphoric acid, and then my colleague Gabriela is going to discuss the results and the conclusions that we did at our research center in Campinas, in the city of Campinas, so that we can share with you the application of this software or program. Ecolab last year celebrated its 100th anniversary. It's present in over 170 countries. It has 115 productive plants around the world. It has over 47,000 employees, over 10,000 patents. We have 3 productive plants in Brazil, in Barueri, Suzano, and Franca. It has over 1,500 employees, and among these, 800 are sales and services representatives. In Brazil, we have 12 business departments, and among these 12 departments, we have the mining department in which we work. Talking about the mining department, we have research centers in the USA, in Chicago, and that's our headquarters. We also have one in the city of Campinas in Brazil. We have one in Australia and one in Shanghai. And we also have many support labs for our clients, and we have some examples of the clients that we have, okay? And that we offer and render services to them. So now, joining the phosphate world, the programs that we have for the phosphate industry, they are very vast and broad. We have for flotation, plant collectors, synthetic collectors, frothers. We have optimization of these products for each mine, for each deposit. We have research and development, okay? We have the CGM, the crystal modifiers, flocculants, coagulants, water treatment at Ecolab. We are world leaders in water treatment, okay? And so we also work with phosphates. We have anti-frothers. We have filter aids, and the filter aids, they were developed. We are going to launch one of them now during this event, specific for the high concentration of apatite. You can go to our stand. There is a pamphlet discussing that, and we also have inhibitors to avoid crusting in our vaporizers. We have this in Mali and in other regions. We want to bring this to Brazil, which is the crusting inhibitors for vaporizers. Now, talking about phosphoric acid, we know that the impurities that can be found in the phosphoric acid, this can impact the creation of crystals, okay? All of these impurities, they come from the rock itself, but they also come from the raw materials. It's important to think about the sulfuric acid, its purity level, the processing water. But when it comes to the removal of fluoride, it's used in diatomite, okay, because it also contains impurities. And so, as I mentioned before, fluoride is present, be it sedimentary rock or igneous rock, and if the finality is for food production, there is a minimum of fluoride. There is a minimum specification that we have to comply with. So this is the motivation behind the program that we're sharing with you guys now. So basically, we have the defluorization, and so you're going to have a reactive silica that is going to react with the fluoride, and then you're going to form silica, and you can use diatomite. And so, what is the difference between our program and the other one? Okay, well, first of all, it's in liquid form. And this helps you a lot. You don't need to prepare it. And you don't insert contaminants into the phosphoric acid because the product is highly pure. You eliminate any ergonomic risks, okay, because when you need to generate and handle the powder or the dust, it's complicated. So you prefer 10 times more to work with the liquid form. High level of reactivity, and so you have a potential to reduce the dose, okay? And so you have to test it, obviously, and it has a high potential to reduce the fluoride grade, okay, in the phosphoric acid. So depending on the fluoride level or grade, okay, it's gonna be better than the diatomite. And finally, it doesn't insert solid particles or inert solid particles, okay, because and which favors the filtration, and so you can achieve gains in your production. So now we're going to present a paper that we did in the city of Campinas to illustrate this product's performance, comparing it to kaolin. This is the system that we created to carry out this analysis. As you can see, we have a vaporizer, and we can control the temperature of that bath, or that we had the phosphoric acid with a certain grade of silica, a certain amount of phosphorus, about between 30 to 40% of P285. And after the condenser, we had the fluorosilicic acid, a little bit of HF, okay, and a little bit of silica. I know that some labs, they also carry out this process, and so I analyzed everything from all of the perspectives. The acid solution that we collect is extremely dangerous for handling, so we have to have extreme care because fluoridic acid, and we can have serious accidents or incidents in the lab. Another important aspect, I believe I'm going to move on to the following slide. So this was an aspect, okay? So we had this balloon that was held at 80 degrees Celsius to reach the evolution level. And so we needed to take care of that. We need to be really careful. Every 30 minutes I got a part of this, 2.5 milliliters, okay? And what is important here? It's not only enough to analyze the fluoride. Inside an evaporator, you need to reach a grade of phosphoric acid that is going to vary, okay, and a grade of fluoride. So the ratio between the P2O2 and the fluoride. And so we go into an evaporator with a ratio of 3 parts for phosphorus for 1 part of fluoride. We have to leave this concentration phase with 100 parts of phosphorus and 1 of fluoride. This is what we want to have, okay? We cannot only trust in the reaction of the reagent. So I use this with an electrochemical analysis, and I analyzed the P2O2, and I did this with a spectral photometry methodology. So this is a simple chart, and we only analyze the phosphoric acid inside the system. And here, the analysis of the fluoride here. And so I did it here that I had a great control of my system. But something interesting that I noticed. How do we remove the fluoride? So we have the fluoride that is combined with calcium in most cases, and then when we add the sulfuric acid into the rock, we have this conversion of this fluoride to HF. HF in most cases. This HF is highly active and reactive, and it's going to react with the silica that we find. And so silicas that are more reactive with smaller grains and a specific size of this grain. Everything that I have inside that system, where's the silica coming from? From the rock or from another part. So I carried out this essay trying to see if I could replicate the system, and I noticed a loss of mass inside the balloon. If you notice, we have 2.7 grams of mass being lost every essay. And so I had 10 essays every day, and I had to change the balloon. So the performance of the product that I am qualifying is going to depend on the silica grade and also the consumption of the glass part, the glass here. So I have a comparative essay here. You can notice the blue curve. That was my control essay with no addition of a reagent, but there was a reduction in the fluoride content because I have the silica from the rock and from the balloon. Okay, we have the 8699, the product. We saw a reduction of the fluoride, and we can see a reduction of the kaolin. And as I mentioned to you, it's useless to only observe the reduction of the fluoride. I have to understand the concentration of the phosphate during the entire assay. And after the 5th cycle, we have noticed a difference. We noticed a difference. Conclusions that we arrived at. The removal of fluoride only happens when there is a lot of silica. And we were able to notice the efficiency of the reagents only after a few cycles, in which the reagent that had the most silica is going to be able to remove the fluoride. So in practical terms, we noticed that our product was able to reduce the fluoride content even with kaolin in the field, in conditions that these two reagents don't do, because of the reactivity of our silica, of our product, which is an active silica. So the conclusions we arrived at, we showed that this methodology is totally adequate. Okay, my work was exactly to prove this, that even with all of these interference we can assess this, and our product showed all of these tests were done in a standardized way, with a standardized grade. And when we had a standardized grade, our product promoted a 60% reduction in fluoride. So thank you so much for the opportunity to speak here, and we are here with our stand, and please pay us a visit. Thank you very much, Rafaela. Thank you.